Solving exponential equations. We'll look at a variety of techniques. Example 1, use like bases to solve. So the technique of like bases is where you try to write both expressions so that they are the same base. So notice how on the right we have a base 3 and on the left we have a base 1/3. I can try to write these so that they're the same base. In fact, 1/3 is the same as 3 to the negative 1. So I can rewrite it, and now they look like closer to having the same base. But they're still not quite the same base because the base on the left is 3 to the negative 1 and the base on the right is 3. But I can use that property of exponents that says that if I have something raised to something raised to something, then I can multiply the exponents. So I can multiply x plus 1 times negative 1 to rewrite this as 3 to the negative 1 times x plus 1 equals 3 to the 5x plus 8. Now, if I distribute that negative 1, I get 3 to the negative x minus 1 equals 3 to the 5x plus 8. Okay, why would we want to rewrite these so that they have the same base? Well, now that they have the same base, we can deduce that if these expressions are equal, then their exponents would have to be equal. Because if the exponents were not the same, then we would get different things when we put 3 to those powers. So the bases are the same, which means we can set the exponents equal to each other. And from here, we can solve for x. I'll add x to both sides to get negative 1 equals 6x plus 8. And then I'll subtract 8 from both sides to get negative 9 equals 6x. And then if I divide by 6, I get x is equal to negative 9 over 6, or x is equal to negative 3 over 2. Okay, let's look at another example. This time we want to solve this equation, 3 to the 5x equals 8. Now, if we tried to make these have the same base, we're going to get stuck, and that's because 8, we can't write 8 as like 3 to a power, so we can't do 8 equals 3 to something, because 8 can only be written as like 2 times 2 times 2. It can be written as 2 to a power, but you can't write it as 3 to a power. So like trying to rewrite them so they have the same base is not going to work. So let's look at another strategy, and here it is. Notice or recall that we have this property that says that if we do log base 3 of 3 to something, that's just going to be equal to the exponent here. The general property is that log base a of a to a power is equal to that power. So I'm going to take advantage of this property, and here's how. I'm going to do log base 3 of both sides of this. The logic is if 3 to the 5x equals 8, if 3 to the 5x equals 8, then if we do log base 3 of both sides, these should still be equal to each other. So I'm taking log base 3 of both sides of the equation. Why would I do this? Because then we can use this property over on the right and basically cancel all this away to get 5x on the left by itself. So I've noticed what the base is on the left. It's 3. And then I did log base 3 of both sides in order to move the 5x down so that it's not in the exponent anymore. At this point, I can divide both sides by 5 to get x is equal to log base 3 of 8 divided by 5. Now this is called the exact answer. This is the exact answer. If we want a rounded answer, we have to type this into the calculator. Now, if we want to type this into the calculator, we're going to have to use the change of base formula. So to type into the calc, we need change of base formula. The change of base formula says that we can figure out what log base 3 of 8 is by doing either log base 10 or natural log of 8 divided by natural log of 3. So change of base formula, it's like we can change log base 3 of 8 into log of whatever base we want of 8 divided by that same log that we used on the top, and then we put 3 inside. So I'm rewriting log base 3 of 8 as ln of 8 over ln of 3 using the change of base formula. Now we can type this into our calculator, and if you do that, you should get 0.3786 if you round to 4 decimal places. So this is called the rounded answer. Okay, so you guys might be thinking that it's kind of a pain having to use the change of base formula to go from here to here. So to do from there to there, we use the change of base formula. If you don't want to remember how to use the change of base formula, there's actually another way to do this problem. So let's talk about the other way. We started out with this equation, 3 to the 5x equals 8. So 3 to the 5x equals 8. The other way to solve for x here is to take ln of both sides. So if both sides are equal, then the natural log of both sides should also be equal. Why would I bother taking ln of both sides? Because if I take natural log of both sides, it allows me to move this 5x to the front here. So that's a log property. So I can put the 5x in the front. And then from here, I can divide both sides by 5 times ln of 3 to solve for x. So if I do that, I get x is equal to ln of 8 divided by 5 times ln of 3. And then I can type this into the calculator where your calculator has a natural log button and you don't have to worry about using the change of base formula. So if you type this into the calculator, you get the exact same answer as we got before, 0.3786, if you round to 4 decimal places. So you get the same answer either way, it's just like 2 different techniques. Let's look at a third example. Okay, we're going to solve 9 to the 5x minus 8 equals 4 to the 2x minus 5. So for this one, there's no way we can write these as the same base because 9 and 4, they don't have any common factors. This is like 3 squared and that's 2 squared, 3 and 2, we can't split them up even more. Now, if I try it like the first way that I did example 2, I would have to either take log base 9 of the left-hand side, but then I'd have to also take log base 9 of the right-hand side. But then that would get the 9s to cancel, but the 4s to not cancel. If I tried to do log base 4 of both sides, I don't get the 9 to cancel away. So I'm going to use my take ln of both sides strategy here. So take ln of both sides. So if I do natural log of both sides, the cool thing is I'm able to move these exponents to the front. So we don't have to worry about these x's being up in an exponent anymore. So the whole point of this technique is so that you can move exponents that have x's in them to the front. Okay, now from here, natural log of 9 and natural log of 4 are both numbers, they're constants, so I'm going to treat them like they are. And we can actually just solve for x. So how do we solve for x? We're going to distribute each side, so I'm going to do 5x times ln of 9 minus 8 times ln of 9 equals 2x times ln of 4 minus 5 times ln of 4. And now I'm going to notice where all the x's are. So we have a term with an x in it here and a term with an x in it here. And then the other 2 terms are constants. So I'm going to get everything with an x on one side of the equation and everything that's a constant on the other side. So first I'll start with the x's. So I'm going to subtract 2x times ln of 4 from both sides here. to get 5x ln of 9 minus 2x ln of 4 minus 8 ln of 9 equals negative 5 ln of 4. Then I'm going to add 8 ln of 9 to both sides so that the constant terms are on the right and the x terms are on the left. Okay, everything on the right is a constant. Ln of 4 is just a number. You could type it in your calculator, and then so is ln of 9. So everything on the right is a constant, and then these two terms on the left have x's in them. How do I solve this from here? Now that you have all the x's on one side, you can factor out an x. So I'm going to factor out the x from the left to get x times 5 ln of 9 minus 2 ln of 4. And from here, I can divide both sides by this entire thing. So if I divide both sides by 5 ln of 9 minus 2 ln of 4, I will get x equals negative 5 ln of 4 plus 8 ln of 9 divided by 5 ln of 9 minus 2 ln of 4. And this is our exact answer. If we want a rounded answer, we can type it into the calculator. And you'll get 1.2962. That's rounding to 4 decimal places. So, general strategy. Take natural log of both sides, move exponents to the front, and then solve for x.